Hello everyone. Before we start today's lecture, let's have a look at your course homepage. And I have already made up this page for assignment one's tutorial sessions. You can go here and book a time slot that is convenient for you. So as you can already see, two of the groups have already taken a slot. So please do the same. Uh, all the other groups, you should do the same. So now let's get started. Today it is our fourth lecture, component-based thinking and architecture styles foundations. So let's get started then. If you have any questions in between, just raise your hand or write a comment in the chat box and discuss with me. Okay. So this is chapter 8 of your course book, and it is about component-based thinking. So let's first try to see what is the difference between modules and components. Well, modules are collections of related code, whereas components are its physical manifestation. So, like for instance, on the right hand side, on the left hand side, you can see a module. Whereas when you kind of combine it as a package or jar file or DLL file or gem file in case of Ruby, jar file in case of Java or Kotlin, or C sharp code, for instance, in form of DLL file, then you will call it a component. So the difference is really just the way you look at it. So you can use them synonymously, but modules really refer to the code that you have, and components are its physical manifestation. Okay, so I just explained all that here. So the scope of the components, where you will find these components. Well, you can find these components like simple wrapper libraries like this one. So it could be a jar file, and inside you got multiple pieces of code. So it's like, wrapping your code at high level of modularity than classes. Or it could be subsystems or layers in architecture. So here is an example of this one. You have one layer, second layer, third layer, fourth layer, and all these layers are of course made up of different pieces of code, classes, packages, and so on. And then you can have a third possibility, such as shown here. It is a service. So over here, it is a service run on its own address or running, and then when it's whether it's running it on its own address on the same machine or in some other machine. In both cases, it has its own address, and then you can talk to that piece of code or service or component in different means, such as TCP/IP, RESTful API, SOAP, service-oriented architecture, and so on. So for instance, this event processor, some piece of code, wants to access this service right here. And so you push your request into this channel, and then actually it's a queue. So when it's your turn, the service will process your request, but for that request, you may or may not want to communicate with the database, and then something comes back, and then it is returned to you. So these are three scopes of components that you can see in different codes. So then comes the concept of architecture partitioning. How can you partition your code within an architecture? So as an architect, what you will do is you will define, you will refine, you will manage and govern the components within an architecture. And when we talk about, common partitioning styles, You can have technical partitioning and domain-based partitioning. So technical partitioning and domain-based partitioning, what they mean, we will talk it in a minute, but usually both of these can appear in layered architecture as well as modular monolithic architectures. What are these? We're gonna look at in the, in detail. Okay, so first we are going to discuss the technical partitioning. So as the name suggests, there is a separation of technical concerns within your code. So you have one layer as presentation, another layer containing all the code related to business rules, one layer containing service, one layer containing persistence, and then persistence layer talks to database, and your data is stored here. So technical partitioning is based on technicalities, as you can see, and the closest you can see is model view controller pattern that matches or that is actually a technical partitioning. So how something happens, how a change happens in a technical partitioning, let's try to see that in an example. So imagine you have a technical partitioning in your code, and your code is about an e-commerce website. So requirements changed, and now you have been told that you have to add an expire date to the wish list items. Like into your shopping cart, you have a wish list item, and before you did not implement it an expiry date, but now you have to implement an expiry date to your wish list items for the customer. What you will do when you want to implement such a thing? Well, probably you will have your you will have a customer table, and if I start from presentation layer, you probably have customer screens where this wish list item has been shown. Then in the business rules you will have some logic related to customer class, and then you will have within service you will have utilities related to customer, and then in persistence you will have some SQL code that would update, delete, insert records in customer table, and here you have this customer table. So in order to make a change in this, adding an expiry date to a wish list item, you have to make the change in this table. Then you have to reflect that change in your persistence layer. And then you have to reflect that change into utilities. Then you have to reflect that change into your business rules. And then you have to reflect that change into your presentation layer. So you see, you have to do all these changes. And because of that, now you need to patch up. Imagine your code is up and running in production. You have to patch up the whole application. So entire application needs a new deployment for a simple feature like that one. So that is, something you need to consider in when you are considering technical partitions. Okay, now let us consider it opposed to with something called domain-based partitioning. By the way, the domain-based partitioning is inspired, this concept is inspired by uh, a, a book written by Eric Evan, and the name of the book is Domain-Driven Design. So what it does is, first of all, the partitioning that you make is based on domains or workflows. So for instance, you will have, since it's an e-commerce website, so you will have one domain or workflow related to catalog checkout. So what you will do, you will have one component containing all the piece of code related to catalog checkout, one module related to the shipment concerns to customers, one module related to analytics, one module related to update inventory, one module related to reporting, and one about update accounts. So it's a domain driven design where you try to make your components based on the workflows within your system. So here is one manifestation of this domain partitioning, what we have seen here for an e-commerce website. You have a database here, and all these components actually communicate to that. However, you have, made them separate from each other. So it's a service-based architecture. We will learn about it in a detail in coming lessons. So you have one component about customer, one component about payment, one component about shipping, one component about tracking, like that. And here you also kind of separated your UI component for customer here. Maybe you are communicating through API calls, maybe you are communicating through RESTful API, it could be anything. And here you have, payment UI. And just to give you a flavor, here we have shipping and tracking UI together, communicating or connected with these shipping and tracking components. And of course, all these components are talking to this database. So by the way, I encourage you to listen to this YouTube short video just to understand domain and technical partitioning in more detail. So what happens if we do the same? So you have a new requirement by your architect. Add an expire date to wish list items. So what you need to do now? Well, wish list items are concerned by a workflow of customer. So you only concerned, your changes are only probably in this area. And the rest of the application will be unaffected. So for instance, it's already there. So let's erase what I wrote. And here now, you will make a change here, customer table. And then you will make a change here in customer component. And then probably you will make a change here in your customer UI. And the rest of your application is unaffected. You see the benefit of domain-based partitioning? Only some components need a new deployment. And since you have separated these components from other, all these components are kind of separated from each other, all you need to do is you don't have to deploy the whole application. You just need to make up, update this database and this customer components. So technical versus domain partitioning, how it looks like in code. So if you think about it, it's really simple. So here we separate presentation layer. So all the things, so presentation layer becomes a package. If we talk about Java or C++ or C Sharp or Kotlin, and then within that you have customer package, and within presentation you have a payment package, and within presentation you will have this shipping package, and within that layer you will have tracking package. So I'm just just to save the space, I'm just talking about customer and payment. So in presentation layer you have both customer and payment. Then in your business layer you have again both customer and payment, business dot customer and business dot payment. And in your service layer, you again have customer and payment. And in persistence layer, you again have customer and payment. That is technical partitioning. Now let us see what happens in domain-based partitioning. So well, you have one component for customer, everything in there. So I'm talking about this customer now here. So what you will have in there is within that customer package, you have presentation layer, business layer, service layer, persistence layer. And then within the payment package, you have, so these are your workflows, the domains. So within that domain, you have all the further layers. And within this domain, you have all these further layers, presentation, business, service, and persistence. So this is what the difference is really between technical and domain partition. Okay, let's apply that to the same case study we have been going through, which is silicon sandwiches. So let me just see if I can find out that details. Yeah, no, it's not here. But remember silicon sandwiches example we were going through. So silicon sandwiches is a sandwich shop, and they want to have an application where people can go to their website or Android application and then order a sandwich. And once you order a sandwich, then either you can pick up from the shop and then a map is shown. Otherwise, you can ask for a delivery and then it will be delivered to you. And they had these concerns like they want to have multiple franchises and they want to expand it and things like that. And of course, there can be a lot of possibilities how you develop your architecture for silicon sandwiches. And one of the possibility could be what I present you here, and it is also taken from your course book. So it's a domain-based partitioning, by the way. So domain partitioning, that means you design around the workflows. So what are the workflows in a sandwich or restaurant based, or let's say in some application, food delivery application? So we have workflows about, let's start from, let's say, recipes. And then we have concerns like local recipes and common recipes, because we wanted to have also at that time some customization, because it's a franchise, and when this franchise goes to Sweden, then there will be some customized sandwiches according to Sweden, and when it goes to United Kingdom, it will have some customized sandwiches related to United Kingdom. So some local recipes and some common recipes. And then you have some make order workflow. You have manage inventory workflow. You have location workflow because it's about maps. You have deliver workflow. You have promotions, national and domestic workflows. You have purchase workflow. So your design is actually kind of formed around the domains or workflows. So here you got discrete components like this one, big ones. And then within that, you got some sub-components, like in purchase, you got order and payment. Okay. But also you can see that you have, some common code copied in many places, like promotion, some common promotions, some local promotions, location, some common locations, local locations. So the common is actually the common piece of code you require, and you have to copy that into many places, as you can see here. So we will talk about this in the coming slide when we discuss the positive and negative things about domain partitioning. So what are the advantages? First of all, it is modeled more closely towards the business functions. How the business functions, you model according to that. So it's about workflows. So easier to build cross-functional teams and domains. So if you have, developer teams, so you can have, one team about purchase, one team about promotions, so it is you can have cross-functional teams around the domains that you have to develop. And it aligns more closely to both modular monolithic architectures. We will talk about that in coming slides or in coming lectures. And it also aligns closely with microservices architecture. This is also something we will learn in lecture number 8. Message flow, how the message flows from different components, how they communicate with each other, matches with the problem domain. And finally, it is easy to migrate data and components to distributed architecture. So each component that you have here, which is designed around domains, you can put them into multiple machines and you can have distributed architecture easily implemented, because these are all can be separated, because each component fulfills a complete workflow. Okay, what is the disadvantage? As we saw, you have customization code here, 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 and here. So, so you are repeating yourself maybe. So that is a disadvantage. So the customization code appears in multiple places. Now let us discuss it against technical partitioning. So technical partitioning says, so if we remember silicon sandwich, we have common concerns and we have local concerns. These are our partitions. Okay. So let's divide. So this is what, design. There can be many designs, but let's focus on only this one. So we have all the local concerns in one partition or layer, or and then we have all the common concerns in one layer. Okay, and then we end up with few things like purchase and deliver. We can't put it in local and we can't put it in common. You just put them in the middle, so these becomes independent layers of its own, because we can't put it here and we can't put it here. So now you end up with a partitioning. So these are four partitionings where it's based on technicalities. So local concerns, common concerns, and then something you can't really put in here and here, you just put it separately in the middle. So common and local represent top level components here, and then purchase and delivery remain to handle the workflows. So purchase and deliver, you also put them in the middle because now they are handling all the workflow by using all these different things. So here also you can see one thing, that in local you have recipes and also in common you have recipes. In local you have inventory, in common you have inventory. So you are kind of repeating yourself, having two multiple components, one for the local concerns and one for the common concerns. So what are the advantages? So it clearly separates customization code, one for local, one for common. And it is more aligned with layered architectural pattern, MVC kind of style. We will learn more about layered architecture in coming days, but you already are familiar with layered architecture. When you implement MVC, then you are kind of implementing layered architecture. And disadvantages are that there is a high level of global coupling. Everything is connected with everything, as you can see. So if I go here and make a change in this promotion, then I have to, since it is, this purchase is dependent on this promotion. So I have actually payment section is dependent on this promotion. I have to make changes here. And since this promotion and this promotion are kind of, two things I have, but representing the same thing, I may have to probably make changes here also. The problem is this global coupling of, between all these layers. You make a change and then you have to reflect that change in all other components or in many components. Okay, now developers may have to duplicate domain concepts. As you can see, we are duplicating domain concepts like recipes, promotion and promotions, location and location, and so on. And you are doing it both in common and local layers. Typically higher coupling at the data level also. Not only you have a global coupling, but at data level also you will have higher coupling. So if you develop a database and you want to convert it into multiple databases for a distributed system, it would be really hard. You have to do a lot of work. Okay, so that is technical partitioning. Some advantages, some disadvantages. So customization is really hard for technical partitioning. Okay. So developers should never take components designed by architects as the last word. All software design benefits from iteration. So what does it mean? So there is this life cycle that we usually go through when we, try to find these components, whether in domain-based partitioning or in technical partitioning. How we find out these different components? There is a technique for that, and let's see what that is. So it's called component identification cycle. So first what you do, you identify initial components, then you assign requirements to those components, and then you analyze roles and responsibilities of those components, and then you associate with those components the architectural characteristics that should be connected with them. And then based on these architectural characteristics and these roles, you may restructure components, and then you again analyze roles and responsibilities, you again analyze architectural characteristics, and you again restructure components, and you keep doing that until you are satisfied. So it is this thing is happening between architects and developers. They are all sitting together having multiple meetings, and trying to optimize their components. Okay, so what kind of methods we have that allows us to do that process? So what I just explained to you what is written, what I explained, what is written here. However, we have precisely three methods to identify components. The first one is called actor actions approach. The second one is called event storming. And the third one is called workflow approach. So through one of these approaches, you can discover your initial components, you can, and then you do the whole process. It's an iterative process. And the idea is that with discussions with your colleagues and, you kind of improve your design. However, when you are identifying components, there is something we need to be aware of. It is called entity trap entry pattern. So before I discuss these approaches in the coming slides, I will talk about what is an entity trap entry pattern. Let's see. So entity trap is, that architect confuses database relations with application workflows. So once you do that, like for each database relation that you have in your database, you try to make a component within your application. If you do that, you will have coarse-grained components. Coarse-grained components are opposite of fine-grained components. So you will not have very nice, components, one for customer, one for maybe some process. So you will have all things kind of connected with each other. So the problem with such coarse-grained components are that once you want to restructure them, it would be really hard. So it is usually called object relational mapping, ORM. So ORM, or object relational mapping, that we do in object-oriented design, it neglects the cohesive design, system design. And usually how we do it, we simply, try to develop our code against simple CRUD operations. And if you want to do that, it is all right. And there are some, tools for that also. One of them is this naked objects. However, this is how it looks like once you do this naked, when you do that entity kind of try to develop through these entities. So like you have options, and by the way, now we are discussing this gone case study, the second case study. I will just refresh your mind with this gone case study, and then I will show you that again. So it's an auction company wants to take its auction online to nationwide scale. Customers choose to the auction and they can participate in, then wait until the auction begins, then bid as if they are in the same room with the auctioneer. Users scale up to 100 of participants for auction, and potentially up to thousands of participants. And there can happen, many simultaneous auctions possible. So if you remember, there is this website, car auction website in Sweden called kvdbill.se, doing the same auctions happening, but without live streaming, video streaming. But the rest is the same concept. You can, select a car, the bids are placed, and, you can place bids and people auction. And finally, when the time ends, the high bidder wins. So this is the same kind of thing. Requirements. Auctions must be as real time as possible. Bidder register with a credit card. The system automatically charges the card if the bidder wins. Participants must be tracked via a reputation index. Bidders can see a live video stream of the auctions and all bids as they occur. Both online and live bids must be received in order in which they are placed. Really important. If I bid first, I should be the first one there. And if you bid second, you should be the second one. Additional context. Auction company is expanding aggressively by merging their smaller competitors. Budget is not constrained, it is a strategic direction. They got a lot of money to spend. Company just exited a lawsuit. So it's really important you do these things right. Otherwise, there can be lawsuits against us. Okay, so that is what we discussed. Now, if you look at it, what we discussed uh, things like auction, customers, bidders, right? So, this entity trap says that look at your entities and build around components around those, like auction manager, so that you can create auction, browse auctions, schedule auctions. Item manager, create item so that you can create item, display item, upload item. Bid manager, so that you can place bids, display bids, track bids. Well, it looks good, but it is not an architecture. It is actual workflows of your system. It doesn't have the workflows of the system. It has just the managers. So how the system manages things. So that is an example of entities, entity trap, we call it. So then how you should do it? Like for instance, here you see when we did that for this technical partitioning, it was not like that. So how should we do it? There are three techniques as we discussed here: actor action approach, event storming, and workflow approach. So actor actions approach. This is the first one we will talk about. Okay, so what is our objective? Our objective is to discover components within a case study. So actor action approach is a popular method for mapping requirements to components. So you look at requirements and then from your requirements, you try to come up with components as always. So this is our common theme. So it provides structured approach for system functionality breakdown. What you need to do is you need to identify uh, who are the actors in my system, and then what are their actions. Actors and actions, as the name suggests here. So it helps uncover typical user interactions. Let me just quickly. So, 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 oops, sorry, give me a second, please. Okay, sorry for that. so, so what you need to do is you need to identify actors and actions. And usually, what it does is it helps you to uncover user interactions. It's a popular formal approach, and let's see how we can do it. But it is suitable for all system types, including monolithics and distributed architectures. How we do it? So we just discussed going on, and we are going to do that for this case study. So first of all, it's a generic solution. So what you need to do is you need to find out actors or roles. Remember that, actors or roles. So what are the actors or roles in your system? One could be bidder, because bidder bids. Action is that bidder bids, but also view live video stream, view live bid stream, place a bid. So try to identify the actor, bidder, we can also call it role, and what kind of actions it performs. View a video stream, view bid stream, place a bid. Then you have auctioneer who will introduce an item in an auction. So auctioneer again actor. What actions it take? Enter live bids into the system, receive online bids, mark item as sold, and maybe few other things. And what is other things? Like it is the system and actor. Start an auction, make payment, track bidder activity, and so on. So through actor actions, you will try to look at the actors in within the system or roles within the system and what actions they perform. And once you do that, you can build your components around those components, actors, for instance. So so these actors interact with the application or system, and through that, this system will initiate the events and try to implement some workflows. So let us see what we can end up with this bidder, auctioneer, and system actors. So don't let's try to consume it slowly. So you got bidder, you find it here. You got auctioneer, you find it here. You got system, and here is your system. And now whatever you identified here, the actions this actor takes, you write them down here. View live video stream, view live bid stream, place a bid. Enter live bids into system, receive online bids, mark items as sold. Put them here. What you identified about the system, you put them here. Start auction, make payment, track bidder activity, end auction. And now, based on these, actions, you build components. Like view live video stream, you need a component about video streamer. View live bid stream, you need a component about bid streamer. Place a bid, you need a component, something called like bid capture. Enter live bids into system. Well, this live bid can also be placed in the same component where a bid is later on a person will place a bid. Mark item as sold. That can go to something called auction session. Start auction can also be there. And then later on, though not that is like track bidder activity, that could be a bid tracker. Auction session can talk to it, and bid capture can talk to it, and this bid capture can also talk to bid streamer. And once someone wins a bid, then make payment can happen through payment. So auction session identifies which bidder wins, and it can take us here. Finally, ends auction. End auction can be here connected, so bid streamer will stop. So you see, through that, what we can do is we can identify components. And here are some more details about these components you can think about. Okay. So I want to take your input here. So how is it going? Are you able to follow me? Any questions you have? Anything you have in your mind? Anything you want to ask me? If you have any question, feel free to, raise your hand. Okay, let's keep going then. So, uh, you see what we did according to this diagram, we identify initial components and then we assign requirements to components. And now we analyze roles and responsibilities. So we have, some initial components. Now what we need to do is we will analyze architectural characteristics related to that. And based on that, we want to restructure our components. So let's see how we do it. So imagine this bit capture component here. You look at your architectural characteristics and you realize that bid capture component is being used by bidder and auctioneer. However, the requirements for both auctioneer and bid capture are different. So this bid capture needs to be really scalable, elastic, and support thousands of bidders. But it is not the case with this auctioneer because auctioneers are few. So based on that, since the requirements of bid capture for bidder and for auctioneer are different, what you can do is by looking at these architectural characteristic considerations, you can separate this bid capture into bid capture and auctioneer capture just to make your design better, like that. So the rest of the things are the same, but what you decided, you separate bid capture. So this one will be more scalable, more elastic, potentially supporting thousands of bidders. However, this auctioneer capture is does not require the same kind of scalability, elasticity, because auctioneers are a pretty less as compared to the bidders. Okay, so what we did, we just incorporated architectural characteristics into our uh, initial components that we identified, and then we change our design or components accordingly. The second approach is event storming. So again, the objective is to discover components. Through event storming, you can also discover components. By the way, this approach, event storming, comes from domain-driven design, and it is a popular technique within microservices architecture and event-driven architecture. What these architectures are, we will study that in lecture 7 and 8. So what it does is it uses event-based communication between components, messages or events. And components emerge from business events, not actors or UI screens. So in actor action approach, you try to look at what are the actors and what are the actions they perform, and you try to model your components accordingly based on that knowledge. But in event storming, as the name suggests, you try to build up components around the events, business events happening within your system. So here is the same example, like what kind of events are happening in this auctioneer system, in this auction system, for instance. So auctions being scheduled, auction started, bid placed, highest bid updated, auction ended, auction won, payment processed, reputation updated. So these are the events. So you just identified events in your case study. And now what you will do is you will build components around these events. So for instance, auction scheduled or auction started and auction ended somewhere. You can have an auction life cycle event, okay, trying to manage start and end auctions. So it will emit messages or events such as auction started and auction ended. Then you can have bidding services. So bidding service, what it does, it accepts bid, place bid, and things like that. So accepts bids, enforces ordering, emits bid placed and highest bid updated, that kind of things. And then you can have bid projections or read model. So what this can do, it can maintain real-time bid view of users. So event-driven read side. And then you can have video streaming. What it does, you can start or stop a live stream of auction started, on an auction ended. So you can have that in video streaming component. Payment services processes the winner payment on auction one. On this event, you trigger this payment service, and then this will happen. And then you can have something like, like this reputation updated. So reputation services updates the bidder reputation on auction completion. So you are probably end up with very much similar components as you did in actor action approach, but these are more based towards the events happening within your system. And then comes workflow approach. So now what you will do in this approach, you center around your, how you discover components. You try to look for the sequential steps or processes or workflows within your system. So you try to see what are the business processes that I should support. So now here you are not looking at events. You are just looking at the workflows, business processes within your system. So what you will do, you will identify key roles and their associated workflows. So for instance here, What are the workflows, the main workflows we have in this auction system? Register bidder and verify, payment method, prepare and start auction, conduct live auction, close auction and settle payment, update bidder reputation. And based on that, you can end up with components like user and registration, auction setup to create auction, schedule, start, stop. You can have live auction execution, runs auctions like accept bids, order them, live streaming, update, etc. Auction settlement determines the winner, trigger payment, finalizes auction. And then you can have reputation management, update bidder reputation. You can update the bidder reputation here after the auction is completed. So three approaches, same concept that what we want to do, we want to identify components. Let us try. So here, components align with business processes, making this approach intuitive for monolithic architectures. So you are more familiar with monolithic architecture. Monolithic architectures are those where everything stays in one place, or layered architectures, such thing like, and style like MVC supported style. So it is more, kind of um, intuitive for these architectural styles. And now in this slide, we are going to just compare three methods or approaches that we studied. So actor action approach, event storming, and workflow approach. So primary focus of actor action approach is who does what. Event storming is about the events, what happened. And workflow approach is all about how work flows. What are the business processes? The starting point in actor action approach is users and system roles. In event storming, it is all about domain events. And workflow approach is based on end-to-end processes, business processes. The key abstraction you have is about in actor action, what are the actors, what actions they perform. In event storming, it is what are the events and what reactions they do. What are the reactions as when the events occur? And in workflow approach, what are the steps and what are the activities against it? In actor action approach, the component is role-centric services. So it's about all the roles like bidder, so place bid and the way like that. And then event storming, it's all about event-centric services, small event-centric services. And in workflow approach, you have process-centric components. The communication style, how these components talk to each other. In actor action, it will be direct API calls. In event storming, usually it is asynchronous messaging or events. And in workflow approach, it is mostly synchronous flows. So you send a request, you wait it to be completed, and then you move on further. In asynchronous message, you send a request and you start doing something else. And later on, whenever that thing is completed, it will be sent back to you. What are architectural styles suitable for actor action approach? It is layered architecture and service oriented. Event storming is good for event driven or microservices architecture. And workflow approach is good for modular monolithics architectures and layered architectures. We are going to learn about these architectures in coming slides. How tolerant these approaches are if you make a change. Actor action approach, medium, event storming, high, and workflow approach, medium to low. And then best use when? When in actor action, you should use that when the system scope is clear and roles are stable. Event storming, when it is high scale, real time system, and it is evolving. Things keep changing. And then workflow approach should be when the business processes are stable and well known. So let us revisit what is architecture quantum. So what should you pick, monolithic architecture or distributed architecture? Monolithic architecture means a single deployable unit, whereas a distributed architecture means that it consists of multiple services communicating via network protocols. So the scope of architectural characteristics determines whether to opt for monolithic or distributed architecture. Okay, so it is the architectural characteristics that will kind of dictate you whether you should go for monolithic or distributed architectures. And we will see more about these things in the coming lectures. Great. So that was our first, component for first thing for this topic. So now it is 53 minutes past 11. So since we finished this slides, so we can take a break now, and then we will be back after 15 minutes, and that would be like 11. Let's make it 10. Okay, 11, 10. Sorry. Okay. Okay, so the next topic we are going to discuss is Chapter 7, Architectural Styles, Foundations. So, okay, so what is the difference between an architectural style versus architecture pattern? So the differences can be confusing, and in many books, you see that these two terms are used synonymously. So how should we differentiate between architecture style and architecture pattern? So try to think of it when you look at architecture style, you can consider it a high level structure of how the user interface and backend source code are organized. So architectural style is a high level, comprehensive, or all embracing structure of your software. Whereas if you look at an architectural pattern resides within your architecture style, and it is a low level design structure. So it can aids, like for instance, aids in forming specific solutions, for instance, about scalability, performance within an architectural style. So we can also try to understand it through this analogy of house versus room. So architecture style is like a blueprint for building a house, whereas an architectural pattern is specific design details of a room within your house that you are building. So architectural style provides the overall framework, whereas architectural pattern provides you a more ready-made solution for a specific design challenge. So both styles and patterns define relationship between components, their relations, and various architectural characteristics. So architectural styles cover everything, and architectural pattern cover few things within that architectural style. So the first one, the most fundamental pattern is called big ball of mud, or also known as spaghetti code. By the way, this image is built from a real code base where, as you can see, the lines suggest the interactions or the dependency between within the piece of code. So as you can see clearly here, by the way, this big ball of mud concept was, or spaghetti code, the concept was given by Foote and Yode in 1997. And it describes the structure, the messiness of this architecture, as you can see. So big ball of mud simply highlights how messy or unstructured your code is, and how this happens. It commonly results from unregulated growth. You started something, you repair things temporarily, and over passage of time, it grows and grows into a big ball of mud that you cannot control. Of course, this kind of code poses challenges related to deployment, testability, scalability, and performance. However, a sad reality, but many trivial applications starts like this when you start coding. Then, historically, we used to have unitary architectures around us. And it was the time when we had these big mainframes computers and computers, software, and computers were actually, a single entity. So mainframe computers, that brings us this architecture called unitary architecture. Over time, what happens, we separated functionality to improve scalability and performance. And usually these days, if you look at the systems, such unitary architectures only exist within embedded systems. And other than that, you don't see that anymore. As networking PCs became common, more distributed systems like client server architecture actually appeared. So with the passage of time, we started to have distributed or two-tier client server systems or architectures. So this fundamental style separate technical functionality between front end and back end. And then it further evolved into different flavors based on computing capabilities and based on time. So for instance, we could think of um, a distributed system where we have desktop and then a database server. We can also think of a browser plus a web server, of course, into different geolocations. We can also have three-tier where it got popularity in 1990s, where we separate database application and we separate database application and front end tiers. And now, when we look at architectural styles, we can clearly divide uh, architectures into two distinct styles: monolithic architectural styles and distributed architectural styles. So, monolithic architecture style means one single deployment unit, whereas distributed architectural styles means multiple deployment units connected remotely. So, different machines, different geolocations, and then you install those units separately. So the examples of monolithic architectures are layered architecture, pipeline architecture, and microkernel architectures. Whereas the examples of distributed architectural styles could be things, architectures like service-based architecture, event-driven architecture, space-based architecture, service-oriented architecture, and microservices architecture. And we are going to look at all these architectural styles in this course. So distributed architectural styles trade-offs. When you should use which one? What are the trade-offs between these two? No one is good or bad. All what matters is that what kind of architectural characteristics or quality attributes you want to support, and based on that, you will pick the most suitable architectural style for your needs, for your quality attributes, for your non-functional requirements. So distributed architectural styles are more powerful than monolithic architectural styles in terms of performance, scalability, and availability. However, when you add, the distributedness into the picture, then there are some significant trade-offs to this power also. And we call them fallacies of distributed computing. And now we are going to look at what are the fallacies of distributed computing. Actually, what are the trade-offs of distributed architectural styles or distributed computing? So let's look at them one by one. Policy number one is the network is reliable. Well, network is as reliable as, when until it is working. So we should, in the time we are living right now, networks seem to be so reliable that we are, dependent on Wi-Fi's. Wi-Fi's are connected with other internet service providers, and everything happens seamlessly. So we go, we tap our card on a point of sale app, device, and then a transaction happens. But as sorry for that, but you may have seen that usually some once in a while, when the network is down, when some attack happens, then a lot of things starts to break down. Like maybe you go to Ecamaxi, you go to Willis, you try to tap your card, and then their service is down, and it can shows this policy that network is reliable. Yeah, most of the time it is reliable, but it is not 100%. So we can say that networks remain generally unreliable despite improvements. So it impacts communication between services and it impacts reliability. Once the service is down, then reliability is impacted. Usually you can think of two services connected with each other over a distributed setting, doing this rest calls and fetching the data from each other. And when network is down, then the both services cannot talk to each other. So the first fallacy is that network is reliable. Yeah, it is true most of the time, but when it is down, everything shuts down. The second one is latency is zero. No, it is not true. Like imagine you have this component A and component B on the same machine. So this time that it takes is local. Local in-memory method call is much, much more faster and instantly it will happen. You have one component and then you have another component. You put them into one, packet. You put them into one application within your Eclipse or within your Visual Studio. You just make an API call and it is so fine because it's happening within your local memory of your computer. However, now consider a service A and service B, and then you have you put these services into two machines connected through a network. And now you make RESTful calls or remote access calls between them in any form. And now this time that it can take for this, data to return on this time, on this remote setting or distributed setting would be much greater than the time it takes to call a service or component or API on a local setting. So time in remote setting is much greater than time in local setting. So that is the second fallacy, that latency is zero. Latency is never zero. Okay, and architects must consider and analyze average and percentile less latencies because these things can impact latency, how much time it takes. The third fallacy is bandwidth is infinite, which is not true. Bandwidth is always finite. So whenever you are working in a distributed setting, you need to be really vigilant about the use of your bandwidth. Only makes calls which are absolutely necessary. Ensure that you make minimal amount of data, calls between two services. Because bandwidth becomes a concern in distributed architectures, bandwidth is not infinite, though we consider sometimes that it is infinite. And then policy number four is that network is secure. Well, most of the time it is secure, but there are a lot of cyber security attacks happening every day. We don't feel it because usually all these major companies and like imagine Calsta University, they have hired companies like T2 Every to secure their networks. So we are spending constant amount of money just to make our distributed computing secure from outside world. So network is not secure. We spend a lot of money, a lot of security, just to look like it is secure. So security challenges are increasing in distributed architectures. And now ensuring security requires that when you have more encryption, you try to add more layers, more firewalls, what happens? Your performance tends to degrade because you need to check additional things in advance before a request is passed to the system. We need to find who is a good client and who is a bad client before this RESTful call can come to this service. So more checks you provide, more security checks, the more expensive or slow your system can become. Policy number 5, the topology never changes. The topology, the inside, the router you use, it changes all the time. You can have it in distributed computing, within a house, within a lab, within a network. You can have some, old routers, you can have new routers, you can have a lot of different kind of topologies over time. And architects mistakenly assume that there is a fixed network topology within between service A and service B, but actually we don't know. These topologies can change because maybe a router breaks down, you put in a new router, and now that has some different kind of encryption, it can have some different kind of things, and that can affect your system, your interaction from this service A to service B. So the topology never changes is another fallacy. So what you need to do, you need to have a constant communication with operations and network administrators as an architect, just to ensure everything is in the way that it should be. Finally, we assume that there is only one administrator in a distributed computing, but it is not true. There are a lot of small administrators trying to control their part of the network. So it is important that we consider, we assume, we remember that there is no one administrator. There are many people in between two services, and you need to talk to multiple administrators to make your service work. And policy number 7 is that transport cost is zero. So transport cost means sending data from one place to another. It is not. So distributed architectures incur high cost as compared to monolithic architectures. The cost can be associated to the infrastructure on which you run your distributed, your services or additional components. So cost is never zero. Transport cost is never zero. So that is the fallacy number 7. And finally, fallacy number 8 is that network is homogeneous. Network is not homogeneous. It is, connected through multiple routes, multiple hardwares, some old, some new. And assuming that you have a homogeneous network is not true. So heterogeneous hardware vendors may not integrate seamlessly. So we need to remember that also. There are other distributed considerations also, like if you want to find out where the fault occurs within a distributed environment, it would be really challenging. Logging the faults, finding the root cause analysis would be really challenging. However, you can have tools like Splunk that can help you with finding out the root cause, doing the root cause analysis. Then, uh, distributed transactions, we need to understand the nature of distributed transactions. So transactions are more complex in distributed architecture because the standard properties of ACID transactions, atomicity, consistency, isolation, and durability, it has usually what we do in distributed transactions is that we give away these to gain scalability and availability. So ACID transactions ensure consistency and data integrity of our systems. However, distributed architectures, what they do, they provide us eventual consistency. Most of the time, it will be consistent, but there can be some instances when we lose our data. So this is a trade-off of distributed systems. Like you or we, when we pick distributed systems, we give away consistency and integrity to gain scalability and availability. So we are sacrificing data consistency and data integrity. If you don't remember what these acid properties are, I have one slide to just remind you. So A is for atomicity, C is for consistency, I is for isolation, and D is for durability. So I'll try to give you an example so that you remember what these properties are. Imagine you buy a laptop of 1,000, maybe, kroners or pounds, and then these are the transaction steps: charge payment, reduce stock, and order, create order record. You see, what you will do is once we buy this, it requires that payment should be charged to me. Then in the stock table, that laptop should be reduced. And then we should create a new object or order record, where we have this laptop with this price, date, and all the other details. Okay. So what is then atomicity? Atomicity means all or nothing. Either all these steps should happen: payment charged, stock reduced, order created, or nothing happens. So imagine payment is charged from my card, stock is reduced, and then some network error happens, and order could not be created. Now what should happen? We should roll back. Stock should be added back, and payment should be sent back to my card. So either everything happens or none happens. So that is called atomicity, all or nothing. So we should not charge money if order fails. Then the second is consistency. Rules stay valid. So database rules must hold. For instance, stock cannot go beyond zero. So it could be any rule that you have within your system. So stock cannot below zero. Payment must match order total. So payment for this laptop is 1,000, so it should match with 1,000. So this is consistency. So system remains correct. So consistency is about rules stay valid. And when you keep the rules valid, your system remains correct. Then isolation, no interference from any other process. For instance, imagine you and me, two customers, check out at the same time, more or less at the same time, for the last laptop. Now, isolation means the system should be able to identify who is the first one, you or me. And whoever that person is, the system should lock in that person with that transaction. So isolation ensures that only one purchase succeeds, no double selling. And finally, durability is about permanent saving of those records. So once checkout is confirmed, then doesn't matter if the website crashes, something happened to our system, distributed system is down, or whatever happens, orders should still be stored, payment should not be lost. So that is what durability means. So these are acid properties that are ensured in monolithic architectures. However, in distributed architectural styles, we go for eventual consistency in expense of acid properties. We sacrifice some of these. So thank you. That was our next chapter. We will keep going. But now we will go for chapter number 7, which is monolithic architecture style. So I will just confirm everything is fine. We are sharing the screen. You see me, you hear me, and then recording is done. Great. So monolithic architecture styles. Chapter 10 and 12, 10, 11, and 12 discuss these topics. So the first monolithic architecture we want to discuss is layered architectural style. And layered architecture style is very much, you are very much familiar with it. So it is commonly known as n-tiered architectural style. It is widely adopted due to its simplicity, familiarity, and effectiveness. It has, a UI layer, it has a backend layer, it has rules, it has database layer, and which makes it suitable for many business applications. And by the way, it is a natural way to develop applications due to Conway's law. Conway's law say that an organization that designs systems are constrained to produce design which are actually the copies of the communication structures of these organizations. So who develop software? Well, these are the software companies who develop software. So software companies usually have teams around, user interfaces, developers. You have a team about backend developers. They have teams about rule developers, and then they have these DBAs or database experts. Based on that, as you can see, how many layers you can have in your layered architectural style: UI, backend, business rules, or persistence, and then database layer or persistent layer. So that brings us here, which is called layered architecture. It has a presentation layer, a business layer, a persistence layer, a database layer. So every layer has a specific role. Presentation is all about UI. Business layer is all about the business rules. Persistence layer is all about how your object-oriented design is converted into the structure that you will have in your database, and so on and so forth. So this layered architecture is actually a technically partitioned architectural style. So layered architecture is always technically partitioned, that we studied in previous slides. So these are some variants or topology. So these are some physical layering or different variants, the way you can arrange your layered architecture. So you may have a separate database layer where your database resides, maybe on the same system or in another system, and then you can have your presentation layer, business layer, and persistence layer in one place, in one component. You can have three components: presentation layer, business layer, and persistence layer together, and database layer. Or you can have everything in one place, in one application package component. So layers of isolation, these layers can be closed or open, okay? So when the layers are closed, how the data flows or request flows. So any request comes to the presentation layer. And since these are closed layers, it should only pass to the next layer, which is business layer. And then it should only pass to persistence layer. And then it should only pass to database layer. So requests pass through each layer if these are closed. Okay. You can also have, by the way, open layers that maybe is necessary for some shared functionality. And we will see that in a minute. So imagine we have a situation like this. So we have a presentation layer. We have a business layer. So a presentation layer has some presentation components. Your business layer has some business components, but also some shared components. What you have as a business requirements, you don't want that presentation layer to use any of these shared components. So what we can do? We can arrange our layered architecture from this to this. Let's see what we have done. We have just introduced a new layer, service layer, and we put all the shared components here. And then we make this service layer to be open. So what closed means? Closed means presentation layer can only talk to business layer. But presentation layer cannot bypass this business layer and talk to this service layer to access these shared components. This is precisely what we wanted. We wanted to control the access of presentation layer. We wanted to stop this access to these shared components. So how we did that? Because this presentation layer can really access anything what you have in this business layer. So we added additional layer, make it open. So now presentation layer can access to business layer, but cannot access to this service layer. All the shared components are here. In contrast to, since this layer is open, this business layer can access service layer. That means these shared components, but it can also bypass, because this is an open layer, bypass the service layer and directly access persistent layer also. So this business layer can access to service layer, but also bypass it and access to persistence layer. So this is what open means. Closed means only one level. So this layer can access business layer can access persistence layer can access database layer. If you want that these shared components cannot be shared by this presentation layer, you can add additional layer, make it open. Now presentation layer cannot access shared components because it must, so both are closed. So it must only access one next layer, business layer. But business layer, since this one is open, can access this one or can bypass and access persistence layer. So this is the concept of open and closed layers. So let's rate this the architectural characteristics for our architectural style. So it's a layered architecture. Partitioning type is technical. Number of quanta it has is 1. Remember what quantum means? In our previous lectures, we define quantum to be independent, something, a piece of software, a component that is independently deployable, it has high functional cohesion, and it makes all the calls within each other, within that are synchronous. So that is quantum. So how many quanta? So quanta is the plural form of quantum. How many quanta we have for in a layered architecture? Only one. So it is always one quantum. It is independently deployable altogether. It has high functional cohesion, and all the calls within them are synchronous calls. You see here, we talked about accessing these layers. All these calls between them are synchronous. This is what this number of quantum means. Okay. So here we are giving them 1 star and 5 star and in between these ratings. So 1 star means, this characteristic is not fully supported, and 5 star means this characteristic is very much supported. Okay. So let's see what we have. So overall cost and simplicity. So layered architecture ranks the highest on overall cost and simplicity. So layered architecture is the most simple one, and since it is so simple, it usually the cost is also really low. So when you should use layered architectural style? Well, when you have a budget and time constraints. When you expect that changes are technical in nature. That means if you have ever changing UI, but it does not really make updates your backend services, backend remains stable, then you can use it. And your team within your organization, software development teams are actually technical areas. So you got some developers related to UI, some developers related to backend, some developers related to database architecting. Then having a layered architecture would be a wise decision. But look at these concerns like deployability, elasticity, evolutionary, fault tolerance, modularity, and scalability. As you can see that the layered architecture do not support these characteristics well. So when to avoid architectural, layered architecture? When uh, uh, when there is you expect that there will be a lot of fast changes expected from you. So the features and things are not um, kind of finalized. So you should avoid layered architecture. Instead, then at that time, if a lot of things are not finalized and it can change on fly, you should go for domain-based architecture. So key points are it is ideal for small and simple applications because these are highly rated for overall cost and simplicity. Deployability, where is deployability? Here. Where is deployability? Yeah, here it is. Deployability and testability right here. Do I have no? So let me just put that myself. So this is deployability and this is testability. These are ranked low, as you can see. And why is that? Because if you remember the example we seen before, if you make just a small change in the way your shopping cart works, you have to update everything from database up to UI. So all the modules will have some changes to it. So you have to retest all the things, all the layers together, and you have to deploy the whole application again. That is why testability and deployability are given lower scores. Now consider other things like reliability, elasticity, and scalability, for instance. Reliability, scalability, elasticity. Then we have evolutionary, performance is here, fault tolerance is here. So these are also ranked lower, as you can see. Why? The reliability is medium. So reliability is here, medium, due to the monolithic deployment and lower testability. Because of it is a monolith and the testability score is a bit low. That is why reliability is a little low. Okay. Elasticity and scalability. Here is elasticity and scalability is here. Why these two are low? Because of the nature of monolith architecture. So it would be not easy to scale it, and it will not be able to withstand the burst of requests. Okay. Then comes performance, and the performance is challenging because of closed layering. Because you got many layers, usually these are closed, and you can end up with a sinkhole anti-pattern. We discussed sinkhole anti-pattern in today's lecture, where we can build upon manager modules around our database relations. Fault tolerance is not supported because if something goes down, everything goes down. And overall, it is really effective for smaller projects, but challenging for where you need, scalability, elasticity, and other things. So that was our first architectural style, layered architecture. And you are familiar with this architectural style because so far, all the developments you have done, all the code you have written, most probably fall under layered architectural style. The second architectural style is called pipeline architectural style. So this is discussed in chapter number 11, and it is very famous, widely used architectural style. So it is a fundamental software architectural styles. It is also called pipe and filters or pipeline architectural style. It is also a monolithic architectural style. It is commonly recognized in Unix shell languages like Bash, Terminal, and so on. And it is also used in all the functional programming languages like Haskell, OCaml, and so on, but also used in MapReduce framework. So MapReduce framework is a kind of framework we use in big data applications. Okay. By the way, it is also a technically partitioned architecture due to the partitioning of application logic into different filter types. We will see what filter types means in a minute. So it's very simple architecture, and I will try to, and by the way, you already know that if you are familiar with how commands work in Unix Bash. So it is illustrated, let's illustrate pipe and filter in this example, with this example. So you got pipes. What pipes do, they connect different filters together. Consider filters to be self-contained, independent, stateless entities or piece of software or components. So each filter is designed to do one single task nicely. Okay. And how you, so this filter can take some data, transform it, and give it to this filter. So a filter can have four types. It can be a transformer because this filter transforms data into another form. It can be a producer. It can look at the data given and produce a new data from it. It can be a tester. It can check some conditions. How much is the, for instance, certain values. And then based on that, it can transform data, separate data, or it can simply consume the data. So consumer. So these are four types of filters you can have. Producers produce data, transformers transform data, testers test data based on some condition and apply some filters on it. Consumer consumes data and builds something new out of it. So I will try to give you one example. And this example is from text handling problem. What it does, what we are going to do is read a file of text, determine the n most frequent used words, and print out a sorted list of these words along with their frequencies. Okay. So this is a command. And by the way, I will explain that command in the coming slide. So this is your first filter. This is the pipe. So in Unix, so this is the command you can write in your bash or terminal. So this is a filter and this is a pipe. This is another filter and another pipe. This is another filter. As you can see, TR for translate. So we are translating something here and here. And then we sort. And this is another pipe. And then we find out unique counts. And then this is another pipe. And then we sort based on some minus Rn. We will discuss that in a minute. And then this is another pipe. And then we do something else. And then we stop. By the way, this command was written historically by Douglas McLaury. He wrote these 6 commands in a bash, which managed to replace the code written by Donald Knuth, 10 plus pages of Pascal code. So Donald Knuth is a very famous guy in computer science. He has written, this famous book, The Art of Programming. It has 3 volumes, and it has also Donald Knuth is also an author of LaTeX language. The LaTeX language, it takes commands in natural in simple text file and translate that into PDF files. So now I'm going to explain how this works, okay? So what we do here is this tr is a translate command. What it means is that translate minus sc. S means successively. All if they appear next to each other, all the inputs successively translate them. C is the complement, the opposite. So what it says, if you find A to Z or A to Z, small or capital, if you don't find, and this C means complement, if you not find capital A to Z, small or capital, replace those characters successively with the new line character. But where data will come from? Here you give the data from input.txt file. And this less sign over here means read this. So from this file, all the text will be fed to this filter translate. So what it will do? It will read the file, this translate, and anything that is not A to Z, small or capital, it will translate it into or replace it with new line character. And now you got another bunch of text. And that bunch of text will be through this pipe given to sort. So sort will alphabetically sort all these words. And now that bunch of text will be given through this pipe to this unique minus C, which will count those words uniquely and put counts next to them. So I just explained all that here. So at the end, when you run this pipe and filter, first filter, first pipe, second pipe, and then the third filter, you will end up with a file with counts like this. Okay. Now I will explain to you, I will give you a demo showing that. Okay, I need to just remove that, hide this one. Okay, and now I need to go to this link. Let's go ahead. So by the way, this is JavaScript Linux. You can run any one of these. I'm gonna run this one. So in your browser, what it does, it's bash. By the way, this is Linux bash. As you can see, I can run Linux commands here. So readme file is here. How can I, let's echo it. So, okay. So less will give me the text of this. So readme command has, these text inside. With Q, I can come out from it. So these are, some files. Let's fetch something interesting and apply these commands on it. So I'm going to write this command wget. So it's a text-based command to fetch some file from a URL. And Project Gutenberg gives you a lot of, books. So I am going to go to gutenberg.org and files, and this is a specific file I want to just download. So wget http://https. The problem is here, I can't copy paste. So I have to write. And then it says, yeah, gutenberg.org/files 19541 19514, sorry, 14/19514 19514.txt. So connecting to gutenberg.org. And now this file is downloaded. Let's see. Do we have this file? Yeah, this one right here. So less 19. So this is, as you can see, a large file containing some kind of book. Okay. So now I am trying to write these commands. So first of all, tr minus sc, a minus z, or a minus z. So I'm saying that whatever is not these characters a to z, small or letter small, instead of those, put a new line character like that. And then I pass data to it. So this file. So data is given, passed to this command, translate filter. And all the words are shown to you, as you can see. All characters, because you had spaces. So wherever a space appeared or number appeared, you put a new line character there. All the successive spaces are, are translated into one new line character. Okay. Then I use pipe. Here is your pipe. And then what I say is that one more thing. Translate anything that is A to Z, convert it into small a to Z. Okay. And hit enter. Now all these words have been, put into small letters. There are no capitals anymore. Okay, so this is one filter pipe, another filter, and then I use another pipe, and here I say sort them. Now all these are sorted, as you can see, and now I say them, count them. So unique minus C. So give me unique words with their counts. Now these are, unique words with their counts. How many times words appear are now mentioned here. And then I say, let's say one more thing I want to say. Yeah, sort minus Rn. Another pipe, sort minus Rn. N means sort them by number that you have over here, and R means recursively or in the opposite direction. So highest frequency go up, lower count goes down. You see, now you have all these words counted based on their counts. All these are ones, and there are a lot, but if I go a little high, I will be able to see the higher counts like this. Okay, maybe I'm a bit still too high. Here it is. Now you see these are now sorted as with respect to the counts. So you see how powerful that pipe and filter mechanism is. So it is so much powerful that you could have done that into a lot of Java code or Pascal code. 10 plus pages of Pascal code is now, I just, use these pipes and filters. And you can run these commands, yourself also. And by the way, this exercise is taken from this book, Speech and Language Processing by Jurafsky and Martin, second edition. Okay, so some examples about pipe and filter architecture. As you can see, Bash supports pipe and filter. All the electronic data exchange tools, they also support, transformations through this pipe and filter. All the extraction, transformation, and load tools, ETLs, they also, support or based on this pipe and filter approach. And then all the orchestrators and mediators, like in some event-driven architecture, such as in Apache Camel, they also utilize pipe and filter architecture. And here is one more example from your course book, from showing how Apache Kafka does it for you. So Apache Kafka can process different kinds of data streams and categorize it into different, data streams. So you have a Kafka here, and let's say the data you receive or capture is coming from Netflix. Let's assume that. So what you do, you just subscribe to this Kafka topic, and all the videos or data within that channel, you can receive it. So service info capture, or it's a producer, it will capture all the things that you subscribe to. There are a lot of channels, lot of things. You only receive first filter that you need. Producer produces the data for your needs. Then you can apply some kind of filter, this tester filter. It applies some kind of test on it, and some data or some values go to this duration calculator. That is a transformer. It looks at how much duration these videos have. And then maybe you can, you put something in a database output format to MongoDB. And then the data flows from this filter to this filter. And this is another tester checking the uptime of your videos. And this calculates the uptime from your data. And then it goes into this consumer that forms that look at the duration calculator, gives you the duration of a video. And that transformer uptime calculator gives you the uptime for that video. And then you store that into this MongoDB. So this is also an example of pipe and filter architecture. And as you can see, we have a clear separations of concern in this example. And the example shows extensibility also. Extensible, this architecture is extensible. You want to, get something more, just add one more pipe here and it will do one more thing. And then you can put it in this consumer filter, filter, and then you can put that also in your MongoDB. So number of quanta is still one. It's one monolith application that filters separations of concerns. It is cost effective, simple, and modular. So you have, like for instance, here in this example, you just happen to have different components like translate command, translate, sort command, or module, unique module, and you rely on them to work on something. It is easy to understand and maintain. If you want to update your translate command, nothing rest will be need to be changed. Only this component will be changed, and the rest will remain the same. Challenges, deployability and testability. So in deployability and testability, you can see it got 2 stars and 3 stars here, because since it is a layered architectural style and it's a modular, it's a monolith, because of that, it has slightly average deployability and testability scores. And it has, medium reliability. If you look at the reliability here, 3 stars, pretty good. Why? Because it doesn't have any issue related to network traffic, bandwidth, and latency. Why not more like 4 star or 5 star? Because it is still a monolithic architecture. So it cannot go in reliability more than 3 stars, because testability and deployability is still the bottlenecks. So it scores very low on elasticity and scalability, as you can see here, 1 star here and 1 star here. It can't scale and it can't be, elastic. If you give them a burst of request that can, put too much pressure on your module, it will crash. And since everything is like, depend on each other, so this command takes data, and then this command is depending on this one, and this command depends on this one, and this command depends on that one, everything will crash. So that is why low score in elasticity and scalability. Limited fault tolerance, I just gave you, one example, one memory crash in one place, and the rest of all filters will collapse. Limited availability, why? Availability is limited here. Let's look at availability here. Okay, it is not written directly here, but availability is low because if your application crashes, it's a monolith, you may take time, to put it back into production. So because of high mean time to recovery, usually it can experience, usually most of monolithic applications, once they are down, it can take some, time to recover. And that was our modular, these were our layered architecture and then pipe and filter architectural styles. So we covered pretty much today, and I think this is good enough, and we can stop here for today's lesson. Let me see. I will just stop the recording here.